In this chapter, we'll look at how measurements are made, including precision and accuracy in measurement, types of common measurements, scientific notation for exceptionally large or small numbers, and interconversion between units. Measurements allow us to describe and compare different items. If we wanted to describe the elephant here, we could use a number of different descriptions. For example, we could say that the elephant was big, or we could say that the elephant was gray. These would be what we call qualitative descriptions. That is, they describe the quality of the item that we are describing. On the other hand, we could also measure the elephant. We could say that the elephant is 3 meters tall, or that the elephant has a mass of 1,000 kilograms. These measurements are called quantitative descriptions. That is, they express a quantity which we have measured. In this chapter, we will focus on quantitative measurements. In order to communicate effectively, it's helpful to have a common set of units which everyone uses. In the scientific community, as in most countries, the metric units are used. These are also called the SI units, meaning the international system. The official unit of mass is the kilogram, although we will more commonly use grams in chemistry, abbreviated as G. Length is the meter, time is the second, and the official measure of temperature is the Kelvin, although again we will more commonly use a different scale, the degrees Celsius. We're mainly going to use Kelvin when discussing gases. As you may know, these units are commonly modified by a series of prefixes to express larger or smaller quantities. This slide shows 5 of the most common prefixes. I encourage you to memorize these prefixes and their meanings if you do not already know them. Their usage is very common, and you should know what they mean. For example, if we were talking about a large mass, we would use the measurement kilogram. Kilogram means 1,000 times as much, so 1 kilogram equals 1,000 grams. If we needed to make a much smaller measurement, we might use a prefix like micro. For example, if we were measuring very small time increments, we might express it in microseconds. We could write this several ways. Either we could write 1 microsecond equals 10 to the minus 6 seconds, or we could write it as 1 microsecond equals 1/1,000,000th of a second. We could also do some algebra and move the 1,000,000 term up to the numerator on the left and say 1,000,000 microseconds is the same as 1 second. Any of these formulations are fine. We could write this as 1 microsecond equals 10 to the minus 6 seconds, 1 microsecond equals 1/1,000,000th of a second, or 1,000,000 microseconds equals 1 second. When we make measurements, one of the key questions that we need to answer is, how reliable is my measurement? Builders sometimes say, measure twice, cut once. That is, it's important to make sure that your measurement is a good one, otherwise you may waste valuable time or materials. When we make measurements, there are a couple of things we need to pay attention to. One is how precisely our measurement is made. For example, if we are building a house, we may only need our board to be measured plus or minus a quarter inch. In this case, we can use a tape measure and just make sure that we read it carefully. On the other hand, if we're creating parts for a high-performance engine or a computer drive, we need a measurement which is much more precise. Two terms are commonly used to describe the quality of measurements. Those two terms are precision and accuracy. Accuracy refers to how reliable the measurements are. That is, if you make a series of measurements, does the average of those measurements align well with the true value? On the other hand, precision refers to how close a group of measurements are. The classic way to visualize precision and accuracy is with a series of targets. Imagine that 4 shooters visit a target range and fire off a round of shots. The first shooter is a professional with a finely calibrated sight. He places a series of shots right around the bullseye. We would say that his shots are both precise and accurate. The second shooter is a good one, but his sight is offline. As a consequence, he fires a series of shots which land very close together, but which don't hit the bullseye. We would say that his shots are precise, but they're not accurate. The third shooter is an amateur, but his rifle is well calibrated. As a consequence, his shots center around the bullseye, he's all around it, but they're spread out more broadly. His shots are accurate. If you average them up, they're all around the bullseye, but they're not precise. They're not close to the bullseye. Finally, the fourth shooter is an amateur with a poorly calibrated rifle. His shots are not only spread far apart, but they're not even centered around the target. This poor sap is not precise, and he's certainly not accurate. So, let's make a measurement. Take a look at this picture and answer this question. What is the diameter of this marble? I encourage you to pause the video, write a number down. Go ahead and commit to it. Okay, so hopefully you've committed to a value for this measurement. In a traditional classroom, I ask people to write down their answer, and then have people indicate their response by a show of hands. Typically, I get responses like this. About 20% of the class will say that the diameter of the marble is 2.5 centimeters. Usually a little larger percentage, maybe 30%, will say that the diameter of the marble is 2.6. Similarly, a large percentage will say that the diameter is 2.7, and then a smaller percentage will be 2.8. I'll also have sometimes a few people that just didn't do the measurement correctly, and their numbers are off in left field somewhere. But these are the ones that we would say are, in general, are pretty well correct. Now notice that there is some difference here. When we report a measurement, the last decimal place we report often has some uncertainty to it. This is acceptable and it's normal for reporting measurements. We often refer to the last decimal as our last significant digit. So here's a question. What if I announced that I could tell by looking at this picture that the diameter of this marble, you ready for it, was 2.642081 centimeters? Okay, at what point am I talking nonsense? Well, I clearly have measured the 2. The 6 is a reasonable estimate. Anything after that, though, I'm blowing smoke. I know the diameter of this marble to 2 significant digits. This is something that you need to be aware of when reporting answers from your calculator. Your calculator will often report a mathematical answer to 6 or 7 decimal points. However, you generally don't know the answer that precisely. Typically 2 or 3 decimal points will suffice for an answer. There are rules for how many decimal points are appropriate to keep, but we're not going to worry about those here. So if we report measurements to significant digits, do we ever want to report digits which are not significant? That is, not part of our measurement? Sometimes we do. Let's briefly look at the rules for which digits are and are not significant, and which digits are needed in order to report our numbers correctly. In general, anytime you have a non-zero digit, this is significant. Similarly, if you have a 0 which falls between non-zero, this is part of the measurement. This is just the digit that falls between 9 and 1. If we have zeros that fall at the end of the number after the decimal point, these are also significant. For example, if we report a measurement as 1.100 millimeters, we are saying that we have made this measurement and that this measurement falls to our best estimate between 1.099 and 1.101. That is, we do have some uncertainty in the last decimal point, and that might be plus or minus 0.001, 0.002. We haven't specified that, but the last reported decimal point represents the precision to which we've measured it. Don't report extra decimal places if you haven't measured them. On the other hand, zeros which lie to the left of the last non-zero are never significant. They're just placeholders. If we're reporting a decimal value, these may be necessary. Now, they're not necessary on this first one. Those are just goofy. On the second one, we do need these zeros to show us where the decimal point is. However, these zeros are not significant. For example, we just measured the diameter of the marble, and we said that the diameter of the marble was 2.7 centimeters, and we argued a little bit about what that last decimal place was. Was it 2.6? Was it 2.7? However, let's take this measurement and convert it to kilometers. If we were to convert from centimeters to kilometers, our value would be 0.000027 kilometers. Now, over here, we measured two significant figures. Over here, have we really measured it any more precisely? No, we've still just measured two digits, the 2 and the 7. The other zeros just serve as necessary space holders to show us where the decimal point goes. One situation which can cause confusion is when a large number is reported with a number of zeros but no decimal point. For example, we might say that a program could cost $10 million per year. This is probably an estimate, but how much of an estimate? This number might refer to a range between, say, $9 million per year and $11 million per year. If you're budgeting, plus or minus $1 million can be a big deal. Or is it between, say, $9,999,900 and $10,100,000? In this case, we know the first four zeros for certain, but we're unsure on the plus or minus $100. With a general number like this, if we don't specify with a decimal point, we can't know for sure how precise this is. There are generally two ways to get around this. The first is to write a number with a plus or minus symbol. For example, we could add a plus or minus value afterwards to clarify. So, if I was describing the mileage of my car, I could say that it's 200,000 plus or minus 10,000 miles. This gives you a range so that you know what the mileage is going to be. You know the mileage falls within that range. The second solution is to use scientific notation. We'll talk more about that in a later section. Now, notice this last example. I've reported my dollar amount to $20,000 and no cents. In this case, I have added a decimal point. With this number, there is no ambiguity. You know that the value is exactly $20,000 and no cents. Finally, uncertainty is part of life and is part of science. The key idea is that we want to be clear in communicating what we do know and what we don't know. A clear usage of decimal places and significant digits helps us to accomplish this.